Sometimes on the SAT, you'll be given word problems having to do with exponential functions. And that's what we're going to look at here. And what I want to show you is where the equation for these exponentials that we're going to use, which I'll show you just for a second, where we get the equation in terms of what's happening with this percent increase and how this percent increase relates to what we talked about just previous in the previous video, that last problem, about how in order to get exponential growth or exponential decay, you have to increase something by a certain percent of itself every iteration, every step of the way. That's what leads to exponential growth. So let's look at this example. Imagine a bacterial colony whose population increases 10% every hour. What equation can be used to model this colony if it begins with 100 bacteria? So let's actually find out what this equation would look like, and this will help us derive the equation that we will use on all of these questions. So we begin at hour 0 with 100 bacteria. How many bacteria would we have at hour 1? Well, it's a 10% increase. So 10% of 100 is 10. You add that on, and you would get 110. So another way to think about this is going to be 110 times 10% added on to that original 110. Or, remember our shortcut, the percent trick, it's the same thing as 110 times 1 plus the percent increase, right? So here it's the same thing as 110 times 1.1. And I'm sorry, that should be 100 times 1.1, and that would get us 110 as our final answer. So I'm going to write it in this form for now on because we know our percent shortcut and it's easier to use here. So what about hour 2? So at hour 2, our new population base is 110, and we're going to increase by 10% of that, right? This is where that exponential growth starts coming in. We're not increasing by 10% of 100, right? We're not increasing by 10 every time. That would just be linear growth. We're increasing by 10% of this new value, which is going to be bigger than 10. So our rate of change is increasing, and it's changing exponentially. So originally we had 110, which we got from 100 times 1.1. But what we're going to do now is this is just going to be 110 times the 1.1. And again, that comes from 1 plus percent of the decimal. That's our percent trick. And this would end up getting us 10% of 110 is 11, so this gets us 121. Notice this is the same thing as if we look at 110. 110 is just 100 times 1.1. We are taking that and we are multiplying that by 1.1. How about hour 3? Well, hour 3 is just going to be 121 times 1.1, which would get us 133.2 after we multiply that. But notice this is just this value, right? 100 times 1.1 times 1.1, which equals 121, and we're multiplying that by 1.1. So what we're doing each time, each hour we go by, we're taking our number, we're multiplying it by 1.1. Each iteration is a times by 1.1. So you can see if we look here, this is just the same thing as 100 times 1.1 times 1.1 times 1.1, which is the same thing as 100 times 1.1 cubed. And notice this is just the h value, it's the number of hours. So you begin to see the formula that appears. The formula that appears is as follows. Y equals 100 times 1.1 to the h. And that shows you over time, as h goes from 1 to 2 to 3 and on, what the population of your bacteria will be. And it comes from this repeated multiplication of 1.1. And notice this is our exponential form, right? It's b to the x, constant to the variable. This term right here is essentially the initial value. Sometimes the initial value is 1, but a lot of times the initial value is something. So in the case of the bacteria, there was 100 bacteria. That's our starting point. And then each hour, we're going to multiply that by 1.1, that 10% increase. And that's going to lead, if you were to graph this, you would get a curve that would look something like that. You get that exponential curve. So it all fits together. And so remember, you're increasing by a percentage each time. So the general formula to remember for your exponentials, whether you're dealing with bacteria, whether you're dealing with money, whether you're dealing with decay of radioactive materials, which we talked about in the previous video, you're going to use this general formula. So y equals a. Remember, this is the initial value. In the case of money, it would be your principal, it would be the money you invested or the money you put into a savings account. In the case of the bacteria or population of something, it would be the population of something. In the parentheses is going to be basically your exponential growth driver, your constant. So you'll need a percent, and most likely they'll give it to you. And then you're either, again, remember your percent trick, going to add it to 1 or subtract it from 1, depending on whether or not it's an exponential growth or decay. So in this case, we were looking at growth, so we did 1 plus 0.1. But if this population were decreasing by 10% each time, you would just multiply this by 1 minus 0.1. In other words, multiply it by 0.9 each time. And then in your exponent, you get your variable, right? So the number of years, the number of minutes, or whatever your time is. And usually it's time. I mean, basically always it will be time, because exponential growth is typically happening in these word problems over time. And let's look at an example. John pulls 15% of the balance of his retirement account every year to pay for his expenses. If the initial value of the account is $100,000, which of the following functions f models the remaining amount of money in dollars t years later? So what do we have here? The beginning value is $100,000, which all of these have. But each year, he's taking out 15% of the value of his retirement account to pay for his expenses. So we have exponential decay. So remember, using our formula, it's going to be 100,000 times 1 minus the percent as a decimal. So 15% becomes 0.15. 1 minus 0.15 is 0.85. And then it's going to be to the t, however many years pass. And that corresponds to choice B. A is wrong because it simply puts the percent in here, which is not good enough. You need to do the percent trick, 1 minus the percent, so 1 minus 0.15. C is if you had exponential growth. So if his account increased by 15% each year, you would get something like C. And D is just something that's not right. So the answer here is going to be B. Now, sometimes in financial situations, it's a little bit different. You have to incorporate something called compounding. What does this mean? Kimberly opens a savings account at her bank, which offers 3% annual interest compounded monthly. She makes an initial deposit of $300. She withdraws her money 6 months later. How much money does she withdraw from the account to the nearest cent? So she starts with $300 in her bank account. She has a 3% annual interest rate. And she pulls it out 6 months later, and she wants to know how much money she has. So notice the interesting thing here. It's an annual interest rate. In other words, each year her account will increase by 3%, but it's compounded monthly. What does that mean? It means at the end of each month, the bank takes her money, her $300, at least to start, and it says, okay, we're going to give her her interest for this month. But she's not going to get 3% because 3% is what you get over the year. What she will instead get for that month is the portion of interest that you would get for a month. So that would be 3% divided by 12 months because there are 12 months in a year. So what she would actually get is 0.25%. And they would take her money, take 0.25% of it, add it to her bank account, and that would be her new balance. And then the next month, again, they would take that new value, 302 cents, whatever it ended up being, and they would add another 0.25% to it, right? They would take another 0.25% of that and add it in. So instead of waiting until the end of the year to give her the interest, they give her interest every month. I might make a video later showing the details about how this works. But I'm not super convinced that you need to go into that much detail for this test. You need to know a little bit about compounding, but I don't want to go into insane detail. I'm just going to give you the formula that you use in these cases, and maybe if there's request for it, or if I see on the new SAT, knowing this in detail would be helpful. I'll go into more detail. But that's the basic setup. So you get your money every month, and what ends up happening is by the end of the year, you have more money in the account than you would have if you just got a lump 3% at the end of the year, because that percent each month is acting on a bigger and bigger piece of your money rather than just that 3% on the 300 all at once. That's the net effect of it. So in any event, what's the formula? The formula is very similar to above. Well, actually, we'll just do it with these. Y is equal to A, 1 plus the percent over 100, what should I call this? Let's call it C to the CT. So what does the C mean? It's basically the same formula above. And probably should do plus or minus, but really it's going to be plus because you're dealing with interest and that grows typically. So I'll leave it as plus, but in theory, I guess it could be minus. So what is this C? This C is the compounding period. We'll actually call it number of compounding periods in 1 year. So in the case of monthly, C would be 12 because there are 12 months in 1 year. If it were weekly, it would be 52. If it were daily, it would be 365 and so on. But all you do is you just divide your percent by that, right? Because you're only getting a 1/12 of the interest each month, not the whole thing. And then you got to multiply this by 12 so that you can basically account for the number of months that you have, number of compounding periods that go by. So how would it work in this case? Well, let's just plug in our numbers here. So y equals 100 or 300 times 1 plus, the percent is 0.3, so 1 plus 0.3 over C, which we've said is 12, sorry, 0.03. And, excuse me, this is going to then be to the 12t because we've got to put that c in the exponent as well. In this case, we want to know, she drew her money 6 months later, so t is going to be basically well, leave it at this. When we plug in, this is going to be 300 times 1 plus 0.03 over 12. This is going to be 12 times 0.5 because it's half of a year. So, yeah. Another way to think about it, you also could do t in months. You just got to be careful. If t is defined in years, then you have to make it times 12. If you want to do it in months, you just wouldn't multiply it by 12. But for our purposes, we're just going to do it as, CT. We'll leave it as that, the basic format. So it's going to be 12 times 0.5 because she's withdrawing it 6 months later, which is half a year. And now we just got to put this in our calculator. So let's do 0.03 divided by 12. So that's our percent. We're going to add that to 1. Now we're going to raise that to the 6th because 12 times 0.5 is 6. And now we take this and we multiply it by 300 and we get 304.52. We want this to the nearest cent, so it would be 304.53 when we round it, and that would be the final answer. So the main thing to know is this general compounding formula. Like I said, I'm not super convinced you're going to see this a lot on the test, but if it comes up, at least you have this formula. Remember, it's the same as above. All you have to do, though, is just divide the percent by your compounding period, which is usually 12, and multiply your t by the compounding period, which again usually is 12, and then t, again, assuming that's in years, you just plug in your numbers and you find your answer. Like I said, if there's more requests for more detail on this, I will, but I'm still waiting to see how the SAT handles compounding. Roy invests his life savings into real estate, purchasing properties with a total initial value of P dollars. Roy estimates that the value of his real estate portfolio increases by 36% every 5 years. Which of the following best represents the value of his portfolio V after T years? So I call this partials because it's kind of related, kind of like compounding to a certain extent. But not really. So the difference here is his value increases by 36% every 5 years. So if we wanted to find out what would happen after T years, so let's say T would be 2, we would have to just find the rate it would happen over those 5 years, divide it by 5, and then see what that rate would be over 2 years. So it's almost like instead of waiting the full 5 years, he stops after 2, so he gets the interest he should get after 2 years, but it's not compounding along the way. It's just stopping at that 2 years or that T years, whenever that is, and he gets that amount. So first things first, if it's increasing by 36% each year, we know it's going to be either A or B because we need it to be 1 plus 0.36. So that's easy right out of the way. P is the initial value, so that goes out front. So now it comes to these exponents. Notice we don't have as a choice 1.36 to the t, because it increases by 36% every 5 years, not simply every 1 year. Because here you could plug in t equals 1, and then it would be increasing by 36%. That doesn't work. It's got to increase by 36% over 5 years. So what should happen is that when t is 5, right, after 5 years, this should end up being 1.36 to the 1, right? Because it's going to increase by that 36%. So what does that mean? It must mean we have to divide our t by 5. And that will tell us how many periods, or even fractional periods, of 5 years we have. And that's why we're going to get choice B as our answer. Now, choice A, multiplying it by 5, that would be if it compounded 5 times in a year, right? That would be what we discussed above. If you had this C, it would compound 5 times in a year. So that if t were 1, you would have 5 compounding periods in that year. That does not sound right. In fact, it's the opposite, right? You are compounding it every 5 years, essentially. So what you need to do then is divide this by 5. And that will give you the fractional period of time. Like if it were just 2 years, you'd be 1.36 to the 2/5, because you're not going to get that entire 36% interest. You're only going to get a portion of it. So this shows you that rate of growth over a period of time. And that's why we would get choice B. So it's kind of related to compounding, but it's kind of its own separate issue. So I just want to leave it as that for now. So this one's going to be choice B, and that's it for exponentials.